And we're back. Let's talk about assignment 4. Mercifully, for both you and for me, you have 2 weeks to do this one. This assignment was born out of 2 assignments from last term. There's an assignment 4 and an assignment 5, and there are a couple questions in both that I thought just weren't that useful. They weren't very fun for you, and they didn't really teach you or meaningfully evaluate you on some stuff, so I just cut them. This assignment is like the content of 1.5 assignments, but you're given 2 assignments worth of time to work on it. So like, you can finally catch your breath. I can too. As always, for 1 bonus mark, you can write your answers to written questions using Markdown or LaTeX. We will be going back to proofs for this one, so get ready for that. The first big coding question is applying a bunch of data structures that you've learned about already and learning how they can be used together. When we were learning about stacks and queues, I talked about how they were rather simple, and as for individual usage, they may seem a bit too simple, but like, trust me, they're super useful when they turn out to be useful in certain algorithms. These are certain algorithms. So you're gonna implement a stack and a queue, also build a binary tree, and then implement algorithms for the binary tree that will use the stack and the queue. But I'm getting ahead of myself. I want to point out something that caused a lot of confusion last term. Usually when you think of what a stack or a queue should store, you think of like ints or something, I don't know. Well, in the real world, whenever stacks and queues are used, they always store some sort of domain-specific object. So like, oh, that was a lot of jargon. They usually store some sort of thing that's useful for the thing you're doing. In this case, you're going to have your stack and queue store nodes of a binary tree. And last term, in the code that I supplied students, I called that binary tree node class node, and that messed with a lot of people's heads because like making a stack with a linked list, so you make the linked list out of nodes, but you're supposed to store nodes but not make the linked list out of nodes. It was weird. So to hopefully make it a bit, oh yeah, question?
On the assignments of the binary tree, but in the assignment files itself, it's just being wants to change that.
Ah, what the heck? I thought I changed it in the code too. I think you should just go with whatever the assignment files are saying, but I'll double check it against the classes, like the tests and stuff that I'm giving the markers, because the important part of all this naming rigmarole is just to make sure that the markers code is compatible with your code. Clearly, I want this to say binary tree node, but if the code that I'm giving you is just going to say node, you're probably going to have to just go with that. But I'm not going to give a definitive answer right now, because I want to look into it and figure out if I can change it without causing a mess. Yeah?
Can we expect a nice announcement whenever you find out what you want to do.
Sure, yeah. Definitely in class, probably on the course website. If I decide to do nothing, I'll probably just say it in class because the issue only came up in class. Actually, no, it's an issue that affects everyone who both read the assignment outline and downloaded the codes, so I'll talk about the resolution in an announcement. Well, I guess it's getting confusing either way. But to go back to the thing I wanted to talk about, if you choose to make your stack or queue using a linked list, and by the way, it's up to you to choose the data structure you use to implement it, your code would look a bit like this, where you have a linked list that stores binary tree nodes. In the sole context of the stack and the queue questions, this is a super dumb way to store data. Like, why not just store it directly instead of storing a reference to it and also two null pointers? But it's going to be very valuable in the binary tree questions. Another thing worth pointing out is that the ADT you implemented in the previous assignment, the inventory, that was tested for you. I basically gave you a specification in the form of tests, and if it passed all the tests, I could guarantee it would get all the marks. This responsibility is like pushed onto you this time. This course isn't necessarily about tests. You will learn a lot more about what makes good tests in future courses like software engineering. But it's a good idea to start getting experience in this now. You'll be making your own test suite, ideally modeling it off of the test inventory class from last time, and handing that in along with your stack and queue. The markers will be evaluating your classes according to their own test suite that I wrote, but the details of that will be a mystery. You'll have to make a test suite that is thorough enough to make you confident enough that your stuff works. And then moving on to the binary tree, part A is just like implementing the stuff we learned about in class. If you got that quiz question about the successor method right, you could totally reuse it here. The class that you're given will have method stubs for stuff like add, delete, and search, and you'll have to do all that. Additionally, you'll have to make tests for it, just like the stack and the queue. The fun part, finally, is writing algorithms to traverse the trees. There's a depth-first traversal, which should be familiar to you. This is the pre-order traversal covered in a previous class. And a new type of traversal called the breadth-first traversal. The breadth-first traversal visits all of the nodes at each level of the tree before moving on to the next level. Both methods should return strings containing all the numbers stored in those nodes in depth-first or breadth-first order. The place where those extra data structures actually get used is to avoid using recursion. Yeah, recursion is kind of a memory hog on actual computers, and it's also kind of an opportunity to flex your knowledge of data structures. The depth first traversal, we saw that we saw a recursive implementation of it. I think it went like act on the current node, recursively search the left subtree, recursively search the right subtree. That, it turns out, is possible to do without recursion, but it requires either a stack or a queue. Likewise, breadth first traversal, I might just be forgetting something, but I don't think that's possible to do recursively. Don't quote me on that. Iteratively, however, like using loops instead of recursion, that uses either a stack or a queue. I'm going to be a bit frustratingly obtuse about this. I'm not going to tell you which data structure is used for which traversal. Just like, start thinking about it. Somehow, the properties of stacks and queues and the order in which items are removed relative to how they're added, turns out it corresponds to the order in which you visit nodes in a depth first or breadth first traversal. Once you figure it out, you're going to be like, whoa. And then write tests. Basically, make an example like this one. In fact, I think my tests use the exact example that's on the assignment document. Make sure that it gets the right results. Also throw in an edge case, like making sure traversing an empty tree gets you an empty string. Something like that. So that's like the first big part of the assignment. Pretty cool progression, if I do say so myself. Make a stack, make a queue, make a binary tree, use them all together. Yeah? Let's see. Ooh. Okay, so my intent for this was to only apply it to 3B, but I want to think about that for a moment, whether that would be an interesting or worthwhile restriction for 3A. Yeah, I guess all of those methods have some sort of meaningful recursive implementation, like figure out which branch of the tree you're supposed to go on and then just run that method recursively on that side of the tree. But honestly, I don't really care. No recursion allowed for 3B, certainly. Not using recursion is the point for those. But like 3A, recurse, loop, I don't really care. Okay, moving on. This next question does something that doesn't depend on the previous questions at all. However, it uses a data structure that we won't cover till later this week. I think in the way the class was originally set up, we wouldn't cover this data structure for until next week, which sounds kind of catastrophic. So I reordered the lectures a bit so that we would cover it by the end of this week. The data structure in question is a heap, and it's useful for implementing an ADT called a priority queue. Think of a patient waiting room at a hospital. You want to treat the patient whose care is most urgent. You would use a priority queue for that. I'll go into more detail about it at the actual lecture. In this question, you're making a hotel booking site, and you're going to use a priority queue implemented using a heap to give the user prioritized results about hotels based on a metric you choose. I think the options are distance and price. I guess you could compare hotel names too, but that probably isn't very meaningful for most shoppers. I copied most of them from Hotel Mario. Yeah, so you'll be using a priority queue to reorder hotel listings and also making up your own merge operation to do a sort of thing that I could imagine being useful on a hotel booking site, taking prices from multiple different sources and then organizing those based on what the user wants to prioritize. This will become more meaningful later this week when we actually talk about heaps. The stuff we talk about today, if I even get to it, will be more meaningful for the first written question. Yeah, proofs are back, baby. We're going to do some proofs of asymptotic growth results of different data structures. In question 5, you're going to prove a thing that I'm going to assert repeatedly and sourcelessly throughout the next lesson, which is that 2-3 trees are always balanced. The height of a 2-3 tree with n nodes is always in big theta of log n. Contrast that to a binary tree where it's balanced in like the best case, maybe even the average case. But in the worst case, its height can become big theta of n. I suggest a bit of a structure for you and give you some facts that you could use without proof, but it'll be up to you to sort of fill in the meat of the proof. The basic structure is to reason about the lowest number of nodes that a 2-3 tree of a certain height can have, and the greatest number of nodes that a 2-3 tree of a given height can have. Show that they are always asymptotically related to log n, and then use that classic if and only if property to show that those relationships to log n being big O and big omega in all cases make it so they're always big theta. Besides the facts that I'm giving you, this is supposed to be only based on the definition. Then finally, the last assignment question of the entire course has you prove a similar property for a generalization of trees that you may be already familiar with, graphs. Basically showing that the maximum number of edges in a graph is in big theta of the number of vertices squared. Again, this will become more meaningful by the end of the week. And you'll prove this in multiple ways. One is to do so using the definition of big theta. Another is using the asymptotic properties that we learned about near the end of that unit. And the last is that bonus question again, showing it using limits. The first and the last one are like straightforward enough, but that asymptotic properties one, when I was making the answer key for that got way out of hand because I just straight up couldn't figure out how to prove it with the properties that I had given you. It seemed to need some extra properties that the readings didn't mention and that could not be proven from the facts in the readings. So, in parts C, D, and E, you'll be proving new asymptotic properties that go along with the stuff from the readings that will be necessary alongside the stuff in the readings to prove the thing we want with that sort of properties-based proof structure. Stuff like if f is in big O of h, then f minus d is in O of h for any function h. Like, that wasn't in the readings and can't seem to be proven by anything in the readings. If you just want to get this assignment done and run, you can just use these proofs without proof. Trust me, bro, they're true. But to earn quite a few bonus marks, you can also prove them yourself. You'll have to use the definitions to prove them. Like I said, I couldn't figure out how to do them from the properties. You're certainly welcome to try. I don't want to say they're impossible because proving that would be a task unto itself, but I'm pretty sure it's impossible. Proving these from the definitions, however, is totally doable. And while it's not required for this assignment, you could get some pretty sweet bonus marks from proving them yourself. Okay. That was a lot of course-specific stuff. I think we're finally ready to actually talk about 2-3 trees. It'll be a total crapshoot of whether we'll be able to finish the lecture by the end of the class. But like I said, if we fall behind a tiny bit, I'm confident that we'll be able to catch back up. As I talked about on Thursday, 2-3 trees are trees, like binary trees, but they have a different definition that forces them to be balanced and also forces us to kind of complicate the algorithms for the big three, inserting, searching, and deleting elements. I don't want to spend too much time on this because this was the end of last week's lectures, but every node will have either 0 children, if it's a leaf, 2 children, or 3 children. Note that it's impossible for a node in a 2-3 tree to have just 1 child, and that every interior node has either 2 or 3 children. That's where they got the 2-3 tree name. Fun thing to do to convince or to let these lessons sink in is to attempt to make an unbalanced 2-3 tree. You can't. It would require some nodes to have, some nodes to have the wrong, hold up. Okay, I'm not sure how confident about this I want to be. I was about to say that it's totally impossible to make an unbalanced 2-3 tree, but I'm not completely sure if that's true. What I am completely sure of, however, is that once we learn about how like numbers are stored in 2-3 trees and the operations for inserting and deleting them, it will be impossible to make an unbalanced 2-3 tree playing by the rules that I'm about to show you. But with this definition, I don't know, maybe you could like get away with giving some of these nodes children on this side and then like not giving children to this side, and then the result will be unbalanced. Yeah, I'm not completely confident that this definition guarantees that the tree will be balanced, but I am convinced that the operations we learn about with how it stores data will force the tree to be balanced. So let's learn about how data is stored in 2-3 trees. With binary search trees, we had the binary search tree property, and we're going to have something similar in 2-3 trees. It won't be the exact same because like, how the heck is the binary search tree property supposed to work for a, well, trinary tree? Doesn't map exactly, but it maps similarly. The big idea is that every node can contain either 1 or 2 data values. And if it contains 2 data values, they're sorted amongst themselves so that the first one is less than the second one. So you could have a node that looks like 3, 5. That's good. You can't have one that goes like 5, 3. Nuh-uh. Oops. I said nuh-uh. And then since we use a strict inequality, we definitely can't have a node that looks like 3, 3. We saw recently that duplicates break binary search trees. They break 2-3 trees too. And the number of values that a certain node has is related to the number of children that it has. If an internal node contains 1 value, then it will have 2 child nodes, like all the time. It can't have 2 values and 2 child nodes. That'll break the rules. If we let TL and TR be the left and right subtrees, then this whole thing obeys the exact same rules that binary trees did. Everything here is less than the value here, and everything here is greater than the value in here. It's what you know. And then if the node contains 2 values, then it will have 3 child nodes. And the way that the values are arranged is a little weird, but you'll find that it's a sensible generalization of how binary search trees work. The values in the left subtree are less than like everything to the right of it. The values in the right subtree are greater than everything to the left of it. And then we also have a middle subtree. These are going to be, or this is going to contain values that are in between everything, including these 2 data values. I don't feel like drawing my own example, so check out this one. In the root node, we have two values, 11 and 22. Everything in the left subtree is less than 11. Everything in the right subtree is greater than 22. So like they follow the rules of typical binary search trees, having left subtree have lower values and right subtree having higher values. And then the new thing that you have to understand now is that the middle subtree contains values that are, how am I going to represent this? Greater than 11 and less than 22? Good enough. They're between the two values of the parent, the middle subtree. This applies to other nodes, of course. We see this node has values 2 and 8, and the values in the middle subtree are between 2 and 8. And then something that I want to sort of like emphasize, because some students don't remember this and it leads to bad performance on questions about this. Remember the correspondence between number of data items in a node and number of children of that node. If it has 2 data items, then it will have 3 children. If it has 1 data item, it will have 2 children. So I guess a decent generalization of this is that for all interior nodes, the number of children is 1 greater than the number of data items that it has. You could remember that. You could just memorize that it's either 1 data item and 2 children, or 2 data items and 3 children. Whatever works, it works. Just remember that, and that all interior nodes have children, and all the leaf nodes, by definition, don't. That's the combination of properties that makes it so these trees are always balanced. The search operation works very similarly to binary trees, but with like just a small additional complication with the fact that occasionally we're going to have to go like directly downward instead of left or right. So for this example, let's look for the value 19. Of course, as humans, we can see it's right there, but computers don't have that kind of vision, at least the computers that you're programming don't. So we'll need to make an algorithm that works based on the data it has to find that value that it wants. It starts at the root because a typical 2-3 tree class will only give you access to the root. So we're going to start there. With a binary tree, we would have just one value, and we would look at 11, find that 19 is greater than 11, and go right. Slight complication. We have 2 values. We're looking at 11 and 22. We see that 19 is between 11 and 22. So we're going to go down. In code, we would access the middle child of this node. Now we're looking at a node with 1 value. If you implement this recursively, then you'll be like actually actually just looking at this subtree. And luckily, the node that we're looking at, the root of this subtree, that just has one data item, 2 children. So we can go back to the simpler case. Just check, is 19 less than or greater than 18? It's greater than, so we move to the right. This should help sort of sink in the relationship between number of data items and number of children. Like say 18 had 3 children. Like in its class for a 2-3 tree node, all of its pointers were non-null. Under what conditions would we look at the middle node? None that I could think of. It just doesn't make sense for it to be there. Likewise, if we had 2 values in that root, but only 2 children, we wouldn't know what to do for values that are in between 11 and 22. Either the left or right subtree would be choices that you can argue for, but both of them would be wrong. If it has 2 values, it has 3 children. If it has 1 value, it has 2 children. All the time. Unless it's a leaf, in which case it always has 0 children. So we went to the right child of 18. We're at a node with 2 values, and one of them is the one we're looking for. So we found it. Yippee! So this is a sort of summary of the search operation for 2-3 trees. You should understand how this algorithm works, like be able to execute it if I give you a piece of paper with a 2-3 tree on it and I tell you to find 5 or something. But you don't need to like memorize this. My first year comp sci instructor, more specifically my Comp 1020 instructor, liked to say, memorize nothing, understand everything. So you better understand this. I'll go over it as a quick summary. If a node contains 1 value, apply the same logic as searching a binary search tree. If it contains 2 values, apply slightly more complicated logic. Move to the left if the key is less than both values. Go down the middle if the key is in between the 2 values. Or go right if the key is greater than both values. Search ends when either the key is found or we reach a null pointer without finding the key. This last bit is just like binary search trees. Okay. The insert operation is kind of where the magic happens, because it's like I was talking about earlier with how you could probably make an unbalanced tree using the definition found earlier based on just like how many children each node can have. But following the rules in this insert operation is what makes it truly impossible for it to be unbalanced. And yeah, we're gonna insert a bunch of values in order to see how this works. And in parallel, I'm going to also draw, hello, where'd my new note go? Boom. I'm also going to draw what these operation results would look like on a binary tree, just for fun. We're going to start from nothing and insert the value 1. We create a node to hold this value and make it the root node, I'm just going to draw a little header binary tree. Okay, we have our root node containing 1. Now we're going to insert 2. Ignoring this for a moment, in a binary tree, inserting 2 is as simple as making 2 the right child of 1, because 2 is greater than 1. In a 2-3 tree, it's actually a bit simpler. 2-3 tree nodes can hold either 1 or 2 values. So we just put that new value in the same node. So this is our 2-3 tree, and this is our binary tree so far. Now we're going to insert the value 4. In a binary tree, we just search for 4. The search will fail, and then we put 4 in the place where we expected to find it. In this case, 4 is greater than 1, so we move right. 4 is greater than 2, so we move right. Nothing there. Where'd the undo buttons go? Huh. Weird. We're going to put it here. Now, for the 2-3 tree, you might think that we would want to do something like this, but that would make it unbalanced. Right side has 1 node, left side doesn't have a node. Middle side doesn't have a node either. It's a mess. We don't want this. But the alternative doesn't really work either. We're going to add that value to the leaf to make 1 node that has all of the values, 1, 2, and 4. But that just breaks the rules. The 2-3 tree, not a 2-3-4 tree. Nodes can have 1 or 2 values, not 1, 2, or 3. Whatever, numbers are confusing. The point is, this isn't allowed. Bad. But it is a necessary middle step. We're going to insert that value anyway, end up with something that isn't allowed, and then we're going to split the node. Splitting a node involves moving the middle value upward, and then those 2 extreme values become the children of the newly moved upward node. What will that look like? Looks like this. Much better illustration than anything I could have thought of. You could pretty clearly see that the middle value becomes the new root, and those 2 extreme values became its children. And the tree is balanced. It's a miracle. So let's keep going. We're going to insert 11. That goes into the same root node as 4, because we search for 11, we can't find it, but we know that it should be around here. That node where the search stopped just had 1 value in it. It had room for 1 more, so we put it there. Meanwhile, in our binary tree, we search for 11. The search fails right there. 11 is greater than 4, so we add it as our right child. Insert 13 in the binary tree. 13 will end up as a right child of 11. And in the 2-3 tree, we're going to add it to the node containing 4 and 11, because in a search for 13 inside of this 2-3 tree, the search for 13 would go this way because 13 is greater than 2, and then attempt to go this way but fail because 13 is greater than both 4 and 11, but the node, or the path of node stops there, so it fails. So then we insert it. This root node now has 3 values, 3 data items, as I was calling them earlier in this lecture. Values is a way nicer name, though. 3 values, that's bad. We need to split up the node so that we can follow the definition of each node having either 1 or 2 values. And that follows the same procedure as the split that we did earlier. 11 is going to move up, and then 4 and 13 will become separate nodes. Before, there was no parent node. We were splitting the root. So the node that we moved up just became the new parent of those 2 nodes. But that wouldn't really make sense. Would we end up with something like this? Funny bit of terminology here. This isn't required for the course at all, but a graph like this that is disconnected, but such that all of its connected components are trees, that's called a forest. Clever. But we don't want a forest. We want just one tree. So the trick here is that we're going to move that new node up into the root. 11 will join 2, and then 4 and 13 will become siblings of 1. And the result looks like this. Still balanced. I think I'll do one more insertion. Yeah, inserting 18 just goes into the same node that contained 13 before. And in the binary tree, it would look like this. So last thing before we go, just sort of like look at these. Notice how the binary tree is shaping up to be a complete disaster. If we wanted to search for the value 18, we would have to go through all of the values, O of n. But the 2-3 tree is still balanced. Every single possible path we could follow during a search is still relatively short. Log n height. So that's pretty neat. I probably won't continue this binary tree example next class, even though I will continue the 2-3 tree example. I just wanted to show you how the edge case that destroyed binary trees earlier doesn't make the 2-3 tree break a sweat. So that's all for today's class. We'll cover 2-3 trees a bit more tomorrow, and see you then.